Somewhere tonight, a 3,000-ton bridge is rolling down a closed highway at walking pace. A finished span rides on hundreds of small wheels, aiming for bearings that must land within millimeters. Get it wrong, and the deck cracks before it reaches the abutments. Get it right, and the road reopens by morning. Watch to the end for the 200-meter span that crossed a live airport apron. Bridges are built for traffic to cross them. Tonight, the bridge itself is the one being driven. A finished 1,300-ton span sits above the interstate on hundreds of small wheels, rolling at walking pace toward its final position. You keep waiting for something to go wrong at that weight. Nothing does. The lanes below reopen the next morning. What used to take months now takes a night. Scale up from a highway, crossing to a full railway bridge over a river, and the trick still works. A 180-meter structure weighing around 2,100 tons is launched across water toward its new resting place, moved as a complete unit rather than pieced together over the current. The engineering payoff is the same principle at a bigger number. Assemble everything on stable ground where you can measure it, weigh it, adjust it, and yell at it. Then move the finished object exactly once. Every meter of assembly done on shore is a meter of work, not done over open water in bad weather. Look under the load and the difference from a normal trailer becomes obvious fast. Each axle line has wheels that steer through a full 360 degrees. The deck adjusts in height by hydraulic suspension, so a tilted road surface becomes flat where the load actually sits. Try that with the flatbed you rented last weekend. Forward, backward, sideways, diagonal, even rotating in place around a fixed point. A pedestrian bridge on Christmas morning is not the setup for a heartwarming story. It is the setup for a 12-hour deadline. A 66-meter, 350-ton steel span rides down the street held in a cantilever with 450 tons of counterweight, jacked 8 to 9 meters above the ground so it can clear railway lines below. 3 network rail lines, 2 DLR lines. The most expensive material on this project is not steel. It is the closure window on those tracks. Miss it, and the next slot might be a year away. But why go to this much trouble in the first place? Because on a modern project, the most expensive thing on site is rarely the concrete or steel. It is the closure clock ticking above your head. The interstate below this bridge carries roughly 112,000 vehicles a day. The old bridge above carried another 43,000. Traditional replacement would keep lanes closed for 5 or 6 months. Using an off-site build plus a moved span, the closure shrank to about 3 weeks, and the final rollover of both halves happened in a single 12-hour window. Each half weighed around 1,500 tons. Call it more than 40 fully loaded semis stacked into one deck. The workers building off-site are not dodging traffic 6 inches away from their elbow. The quality of the pour goes up because the crew is not spending mental energy on staying alive. Before anything new rolls in, the old structure has to leave, quietly, quickly, and without dropping anything expensive into the water below. Deck panels get cut out between girders first, then a diamond-tipped wire saw slices out the girders themselves. Once the girders are on solid ground, hydraulic shears go to work, chewing through rebar like it was string cheese. Pier substructures come down next. Every ton removed cleanly here is a ton the closure schedule does not have to absorb later, and every hour saved in demolition is an hour the reopening deadline gets a little less scary. Over water, the same job gets harder. Concrete spans weighing around 1,800 tons sit up to 33 meters above the river. Jack-up towers on twin barges lift them down to a workable height before excavators eat them piece by piece. Sometimes the reason to move a bridge in one piece has nothing to do with traffic and everything to do with keeping the past intact. A 1920s swing bridge, 100 feet long, 28 feet wide, was moved 1.3 miles down public streets to a park, coordinating 14 different agencies to hand off a single load. 14 agencies had to coordinate every step because the bridge only moved once everyone else did. At the top end of the demolition scale, a 5,000-ton steel arch bridge over a highway is not something you disassemble with hand tools. A custom gantry system lifts the arch off its supports, lowers it onto a barge, and floats it downstream to a heavy lift terminal where the real cutting begins. Torches, hydraulic shears, and self-propelled modular transporters, or SPMTs, finish the job on solid ground where Crestabue can actually stand still. Every operation done at the demolition yard, instead of over live traffic, is one fewer decision that has to be right on the first try, and every kilo of steel recycled here funds a small chunk of the replacement build. Even when the old structure stays, the parts underneath do not. Bridge bearings age faster than the deck they carry. Synchronized jacks lift the entire deck a few millimeters, old bearings come out, new pads go in, and the load transfers back down. Before any moved span arrives, the ground has to be ready to receive it. Excavators strip topsoil, cut down to bearing layers, and load dump trucks in a continuous loop. This is the boring part of the video nobody makes a highlight reel about. But skip it, and the new abutment sits on the wrong material, and the closure window closes on a bridge that cannot be handed over. With the ground cleared, each pier is prepared for the bridge above. Pot bearings, elastomeric pads, or seismic isolation devices are aligned to survey marks and anchored down. These little pucks decide where the load lands, how the deck expands in summer heat, and how much shaking the bridge shrugs off in an earthquake. Get one wrong by a few millimeters, and the moved span will not sit flat when it arrives. A 1,500-ton deck does not adjust itself to a bad bearing. Every hour spent aligning these here saves days of grinding fixes later. So the first part of a bridge move does not start with SPMT. It starts with building a complete bridge in the wrong place, deliberately. Segments manufactured off-site arrive to be assembled like a kit at the project location, next to the alignment where the old bridge still carries traffic. The reason is simple. Staging areas do not have deadlines by the hour. 15 girders, each 222 feet, 9 inches long, and around 277,000 pounds, get lifted by 2 cranes working in tandem. That is how a bridge deck begins, one long ribbon of concrete at a time. Once the girders are in place, the deck goes on top. A concrete pump feeds the mat, a screed machine drags across the surface leveling as it moves, and workers behind it finish the edges by hand. Concrete waits for no one. Miss the workable window and the pour is scrap. The screed rides across the wet surface, its front roller squeezing out excess water, its rotating auger evenly redistributing concrete. Too much water ahead of the roller and the surface loses strength before it even sets. Inside the deck, high-strength steel strands are threaded through ducts and pulled tight by hydraulic jacks. Once tensioned, they get grouted permanently in place. This is what lets a slim concrete section span distances that plain reinforcement could not. Then comes the part nobody photographs, but every driver relies on. A slip-form machine extrudes the concrete parapet in one continuous ribbon, shaping the barrier as it crawls forward. A worker walks behind smoothing joints and knocking down blemishes by hand. You have leaned against one of these without ever thinking about it, which is exactly the point of a good barrier. Water on a bridge deck is a problem you cannot ignore. Curb drainage collects it continuously along the edge instead of dumping it through spaced grates. Less standing water, simpler pipes underneath. And when a completed bridge stretches nearly 900 meters of edge to finish, doing it by hand is not an option. A rolling parapet formwork carries the concrete forms forward on hydraulic winches, letting crews pour section after section with rebar mats loaded from above. The finished bridge sitting in the staging area now needs one more thing: someone to lift it off the ground without twisting it in half. When the finished bridge is ready to move, it still cannot go anywhere. A bridge deck is assembled beside the highway, supported by lifting towers and self-propelled modular transporters. Then the jacks raise the entire structure in perfect synchronization, keeping every support point at the same height. Once the load is clear, the SPMT carry it into place, where the jacks lower it onto the bearings with millimeter-level accuracy. Traffic notices the result, not the process. Four 600-ton strand jacks, each pulling 36 wire strands, lifted a pre-assembled center girder around 70 feet up to final elevation. The river channel below was closed under 48 hours. Now for the awkward part. What if the destination is a live railway you are not allowed to touch? A bridge weighing 2,400 tons and stretching 161 meters is rolled toward its final position on SPMTs, cantilevered over active tracks below. Jack-up towers around 300 tons of lift capacity each hold the deck steady while the transporters slide into position. Laser alignment systems track every millimeter of movement. The two installation weekends ran through September and October. Missed the reopening deadline on the railway, and the compensation bill would build the bridge twice over. The closure calendar is the real client here. And here is where the timing goes from tight to nearly impossible. An airport runway extension needs a highway tunnel underneath, which means two bridges have to leave a live expressway. Available window, 9 p.m. to 5 a.m. That is it. Bridge 1 weighed 150 tons across 21.5 meters, cut clean on both sides, and carried roughly 210 meters to disposal. Bridge 2 was the terror. 463 tons of solid concrete, with a 2-meter height difference between the ground at each end. 3 rows of 15-axle SPMT took the load. 4 larger jack-up units doubled the lift capacity to about 2,240 tons. 2 meters of height difference across the span means every jack has to know exactly what every other jack is doing. The concrete rolled through the fog and made the deadline. This was reportedly the first time this exact configuration had been attempted in Japan. Then the scale jumps again. A 200-meter airside bridge rides 264 axle lines of SPMT across 3.5 kilometers of airport apron. Past parked aircraft through narrow gaps, upslopes. At the destination, the SPMT slide transversely into final position, and the megajack system takes over the last few meters of height. The deck is raised above its piers, held steady, then lowered onto its bearings with millimeter accuracy. Once the bridge is ready to move, the machine that makes the whole footage look impossible steps in, a wheeled system that carries an entire span while still steering like a precision instrument. And now the machine that makes all of this possible finally slides under the deck. A 750-ton bridge in Düsseldorf lifted onto 2 SPMT, no crane involved. Wheels do the work a crane cannot. Look under one of these, and the count starts to feel unreasonable. Rows of small tires stretch farther than the load itself, each axle line carrying part of the deck weight. The turntable modules let the trailer swing tight arcs no rigid truck could handle. A 430-ton bridge segment rides on 24 axle lines to fill a gap over live railway tracks. The operator holds a remote control the size of a car steering wheel. That is the entire control panel, for something the weight of 2 blue whales. Modules slide outward on hydraulic scissors, widening the deck of the trailer itself in minutes. A taller load gets a wider base underneath. Simple physics, expensive hardware. Multiply 44 axles by 40 tons apiece, and the arithmetic gets serious quickly. Every wheel spreads a slice of the load onto the ground below, keeping the pavement within its design limits. Inside every axle line hides a small factory of parts. CNC milled steering pivots, robot welded frames, layers of hydraulic lines threaded like veins through the chassis. The suspension on each wheel adjusts independently, which is how the deck stays level while the road underneath dips and rises. A power pack unit at the back pumps the whole system. Think of it as the engine room bolted onto one end of the trailer. The operator running the remote is not driving in any normal sense. They tell the computer where the load should go, and the computer decides how each wheel needs to turn. That is the only way a machine with 264 axle lines does not tie itself in a knot on the first corner. Now put all that together on an actual bridge site. 2 railway bridges in Finland, one around 500 tons, the other around 1,200 tons, moved by hauling, skidding, and SPMT. The heavier span alone puts every axle group close to its rated ceiling, which is exactly where the hydraulic control matters most. Support frames and grillages sit between the deck and the trailer, spreading the load across dozens of contact points instead of a few. Load a bridge onto the wrong support geometry and it stops being a bridge. It becomes a very expensive noodle. That is the technical concern nobody outside the crew talks about. The deck was designed to sit on its abutments, not on a moving platform. Every point where the SPMT touches the structure has to match a load path the engineers already checked twice. Get that wrong and the deck cracks before it reaches the destination. When the bridge is finally loaded, the tense window opens. The whole span has to travel from staging to final position before the closure clock runs out. 10 p.m. Friday. The interstate closes and the clock starts. By 10 a.m. Saturday, traffic has to be flowing again. That is the whole window. 12 hours to demolish, position, lower, and reopen. The SPMTs roll 2 1,500-ton spans into place, and the highway wakes up as if nothing happened. Months of construction compressed into one overnight shift. Excavators, breakers, and loaders tear through the deck while the sky is still black. Debris hits the road below in controlled piles. Hydraulic breakers punch through the old deck at a controlled speed. Too fast and chunks land on the road below wrong. Too slow and the closure window slips. Loaders scoop the rubble into waiting dump trucks in a rotation nobody stops. Every 10 minutes, another truck rolls out full and another rolls in empty. The rebar cage underneath the concrete gets sliced by shears, then dragged clear so the abutment surface is ready for the new bearings. Machines follow assigned routes, crews work in sequence, and every stage runs to a tightly planned schedule. By the time the last truck leaves, the site is already switching from demolition to installation. There is no pause between the two. The whole demolition finishes before dawn, so the SPMT convoy can start moving in. Multiple excavators work the same section from different angles, breaking concrete faster than any single machine could. Crane picks lift larger sections off in one piece. Every minute here is a minute the SPMT crew is already staging outside the closure zone, engines idling, waiting for their green light. Then the wheels start rolling. The new deck moves at walking pace, workers alongside every axle line watching for slip. Ropes and hand signals guide the operator through the tight corner over the road below. A tiny drift left or right, and the bridge misses its bearings by inches. The whole thing looks unhurried, which is the point. Once it lands over the abutments, the survey team takes over. The convoy has arrived. Now comes the moment that decides everything. A 3,000-ton, 180-meter bridge in Adelaide sits over its final position. 8 250-ton jacks under the deck take over from the SPMT suspension and start lowering. Millimeter by millimeter, the largest object on the block becomes the most delicate. Welders finish the connections as sparks rain down through the dark. The transfer from lift to bearing where every millimeter counts. 16 hydraulic jacks, synchronized from a central control unit, hold the deck steady while the old pot bearings come out. A load distribution plate pressures the new sliding surface down. Liquid metal gets injected into the gap between old and new plates, sealing them into a single load path. The bearing pot itself receives silicone grease on its PTFE sliding face, gets leveled, and is anchored with grout to the pier below. Every one of those steps happens in a strict 5-night window with 0 delay allowed, because the highway above cannot close for the day. Same principle applies at the end of a moved span. The deck lands on bearings that have been precisely surveyed and prepared. A 1,500-ton deck lowered onto a bearing 3 millimeters off center will find that error for the next 50 years. Once the deck is on its bearings, the SPMTs reverse out from under and the joint work begins. Old material is cut and hammered clear, the substrate dried and primed, then a preformed strip goes down to handle the deck's daily thermal expansion. Concrete moves. If the joint cannot flex, the deck will crack instead. You do not want to be the driver above when that happens. The closure pour connects the moved span to the abutments and approach slabs. A slip-form paver crawls across wet concrete, augers spreading, roller compacting, workers behind smoothing what the machine leaves. This is what most drivers actually notice. The last inch of surface, not the 1,500 tons underneath. Grinders roughen the deck surface, dust vacuumed as it flies. A liquid membrane goes down under the asphalt, invisible in the finished bridge, but the reason the concrete underneath survives the next winter. Asphalt goes down in overlapping lifts, each pass tack-coated so the layers bond as one. Rollers work behind the paver, locking density into the mat before it cools. Straight edges, uniform depth. Small things the highway will feel for 20 years. The new deck sits on temporary supports overnight while crews finish edges below. By dawn, traffic is moving underneath. The old bridge closes for the night. By morning, drivers are crossing a new one. Damaged concrete bays get cut, vacuum lifted out, and replaced with rapid cure concrete in one overnight shift. Dowel bars drilled, mix poured, vibrating beam compacting, texture rolled onto the surface before it sets. Temperature probes track the cure until strength gains hit target. Traffic returns before commuters wake up. And here is the fact nobody puts on a poster. A bridge is only as good as the little strips between it and the road. A planer cuts a clean channel along the old joint line, dust vacuumed as it flies. A rotating brush attachment scrubs the channel dry and clean. Moisture here means bond failure later. Bitumen primer goes down first to key the surface, then a preformed strip carries the movement load. This is the material that flexes daily as the deck expands under summer heat and contracts through winter cold. Bauxite aggregate is broadcast across the surface for skid resistance and color match. Then a roller compacts everything into one continuous surface with the surrounding asphalt. The whole operation looks like DIY compared to the 3,000-ton bridge move, and it is. But this is what keeps water out of the deck for the next 20 years. Skip it, and the concrete underneath rots from above. Every layer here is insurance against the next repaving. Instead of wheels, this method uses grease. A 318-meter viaduct in Germany built on a casting bed behind the abutment, then pushed forward one span at a time. Each cycle takes 7 days. Reinforcement pre-assembled off to the side around 40 tons per cycle. Side formwork installed in 4 hours. 270 cubic meters of concrete poured for the bottom section over 6 hours. Top reinforcement laid, top pour completed, then hydraulic jacks push the whole deck forward 20 meters. The deck slides across permanent bearings on temporary launching pads coated with PTFE. This is the calmest bridge move you will ever see. The deck creeps forward at millimeters per minute. No traffic interruption, no closure window, no drama. Different mechanism, same underlying idea. Assemble everywhere except the alignment, then hand the finished object to the alignment in one clean transfer. And finally, the extreme end of the scale. A 6,000-ton concrete box structure. An underbridge, cast on a guide raft next to the operational railway. Then hydraulically slid into position beneath 4 live tracks during a possession window. 6,000 tons, sliding sideways under running trains. Try to picture that number and your brain simply refuses. The offline construction takes the pressure off the schedule. Months of formwork, rebar, and pouring happen where nobody has to close the railway. The slide itself is measured in hours. Once the box is under the tracks, the railway resumes overhead as if nothing happened underneath. This is what the whole discipline is really about. Not the machines, not the wheels, not even the concrete. It is buying back time. Every hour the road stays open is an hour the economy above keeps moving, and that is why an entire industry exists to move finished bridges instead of building them in place. Every hour saved on a closure is an hour returned to the millions of people who drive, ride, or ship across it. The wheels, the jacks, the survey teams, the closure joints. None of it exists to show off. It exists so the road above stays open one more day, one more week, one more year without the traffic pain of the old way. Which move surprised you most? The 5,100-ton Airside bridge crossing an active airport apron, or the 12-hour interstate swap over a Friday night? Do you have an accelerated bridge project near where you live? Drop it in the comments. If this was worth your time, share it with someone who works in infrastructure, and subscribe so the next deep dive lands in your feed. Thanks for watching all the way through. See you on the next one. Take care.